right, now let's take a look at even and odd functions. They're different than even and odd polynomials that you probably remember talking about in Algebra 2. In a couple chapters, we're going to talk about putting these two ideas together, but I do need to make sure you keep them separated. This is an even-odd function. So even-odd polynomial only applies to polynomial. This applies to all functions anywhere for all time. So it's a little broader category. So it's not quite the same thing, but there are some similarities. And so I've got an even polynomial here, f of x equals x squared, and f of x equals x cubed is an odd one. So far you're probably thinking it's sort of seeming like what you talked about with even odd polynomials, but I picked two polynomials that are pretty familiar to us, hopefully, to get the point across. So let me start by taking a look at the graph of x squared, which is just a parabola. And let's think about what we notice about it. Now, usually in class, I stop and get input from everybody. So maybe pause, think about anything you notice, and then unpause and we'll keep going. The main thing that really makes this even is the symmetry we've got going on. And I know you've talked about line of symmetry before, so split this thing down the middle. It's a mirror image on both sides. So let's get a couple points and kind of see what's going on, see if we can nail down something concrete, because we've got to get definitions on this stuff. We can't just say it looks symmetrical. We need an algebra definition we attach to this thing, and it works for every even polynomial ever, guaranteed, no exceptions. So let's plug in 1. I plug in 1 for x, I get 1 for y. What if I plug in -1 for x? Well, I get 1 for y there also. Because I'm trying to see kind of where points that are symmetric to each other might kind of line up. All right, so let me go up to 2. Okay, 2, 4 is a point on this side. All right, what if I go 2 that way? So that would be -2, also 4. And hopefully you're kind of noticing a pattern here, right? Well, no matter what I have for the x, as far as if they're the same absolute value, 1, -1, 2, -2, their y values seem to be the same. You can almost put a horizontal line through it and kind of see points that would be symmetric to each other. So let's see if that holds. 3, 9 would be on there, and -3 would also map to 9. So it looks like we're kind of seeing some kind of symmetry unfold where whether you have a positive or negative value for x, I think in terms of absolute value, you're getting the same y value out. Okay? So let's think about a point in more of a theoretical term. Okay? So for any point, you can put that in there, any point. Well, any point can be defined by an x coordinate, and we could say y, but back to functions, input, output. If I put in x, I get f of x out. When the function has run through, this is the output that I get. So I know you've messed around with y is the same thing as f of x, so hopefully the idea is somewhat familiar. But you want to start thinking about points on functions in terms of x and f of x instead of x and y coordinates, especially for defining this. So key things to think about, well, whether I have a positive or negative x, when I plug it in the function, I get the same y value out. So let's see if this sort of makes sense. If I put in, this is almost too straightforward. If I put in a positive x, then I get that y value out. That's almost too straightforward to even make sense. So let me try the negative version. So if I put in 3 for x, 9 is what I get out. Right, what if I put in -3? Well, I get the exact same y value out. Okay, so that's actually going to end up being our formal definition right there. If something's even, and in a second I've got to draw them out a little bit better. If you're taking notes, just hang on and you'll see it written out a lot nicer. But if it's even, if you put in the opposite x value from what you maybe started with, so instead of 3 I put in -3, I'm going to get the exact same y value out as if I put the positive version of x in there. All right, now let's take a look at this odd function, f of x equals x cubed. And hopefully you got sort of an idea of what that looks like. It's kind of that shape. But we'll put it in Desmos, so we've got an more exact idea. It's actually a little flatter than what I drew in the middle. So I'm going to ask you the same thing. Normally in class, I would stop right here. We'd have a little couple-minute discussion about what do you notice? And I'd take your key points and we put it together. So maybe pause, think about what any kind of symmetry you notice and how we might be able to get a pattern with x and y values like we did on the last part. So what I really want you to kind of notice here is we're symmetric, kind of going opposite directions. So maybe it might be easier for me to just put some points in here and then talk about how to define that. My hunch is you define that in geometry at some point. It's not a type of symmetry that comes up real often, so it may not be one you're as familiar with. But let's say I put in 1 for x. I get 1 out. Okay. So let's put the opposite x, because that's what this is really coming down to. Try an x value, see what you get. Try the opposite x value and see where that point maps to on the other side. Well, that one's going to go to -1. Okay. So let's put in 2. If I put in 2 for x cubed, I get 8 out. If I put in -2 for x cubed, I'm going to get -8 out. So kind of thinking back to the same idea. So if I have some function, this is again almost too straightforward to even make sense. It's a true statement, but if I put in a positive x value, then I get some positive y value out. Let's think of it that way. But what I really want to see is what happens when I put in a negative x value. So I tried 2 first. What happens if I put in -2? Well, the y value I get out is the exact opposite. So negative f of x. And that's going to end up being our definition for an odd. Now I've got a more formal definition for you. So if you're writing this down, don't write that down. That's not as good. So if you're writing these down, these are your more formal definitions here. If a function's even, if I put in -x, I get the same y value out. Okay, it's symmetric over the y-axis. So we saw the parabola kind of, it's symmetric across the vertical line. In an odd function, if I put in the opposite x value, I get the opposite y out. So that's what we call symmetry across the origin. And that's that type of symmetry I said you may have covered in geometry, but it's not one that shows up a tremendous amount, so it might have been a little more unfamiliar to you. Okay, we'll come back to these formal definitions. Let's kind of mess around with this for a second, see what we can come up with, and then we'll get back to the formal definitions. So first up is trying to figure these out using a table. Okay, so I'm going to break here, and I'll magically have these tables completed in a second, and we'll run through it. All right, so if you haven't filled these in already, pause now, go ahead and do these in the calculator, and see if you can come up with whether they're even or odd, and then unpause it, and we'll run through it. So I want to figure out if these functions are even or odd, and I'm asking you to do it by a table. Now this is a good way to get a sense of what's going on, but this is not the conclusive way we always want to approach this. But just to get started, this is probably a good way to think about it. So I've made a table here with a few values. I centered it around 0, which if these things are going to be even or odd, they're going to be centered around 0. What I mean by that is start with 0 and pick some points the same amount above or below 0, like counting by ones. Right? Because if it's going to be symmetric, it's going to be symmetric across the y-axis at x equals 0, or it's going to be symmetric across the origin starting at x equals 0. So that's how you want to center your charts up. And let's kind of see what we got going on. All right? Well, I put in 1 for x, I get -2 for y. I put in -1 for x, I get the same thing. If I put in 2, I get 22. If I put in -2, I get the same thing. So this is looking to be even because when I put an x value in or the negative version, I get the same y value out. So if you tried to graph this, it would turn out to be an even function. Okay, the next one, kind of do the same approach. 1 gives me -2, -1 gives me +2. Okay, I'm just kind of going the opposite way. 2 gives me 38, -2 gives me -38. So if I try an x value and it's opposite, it's a negative version, I get a y value and the negative version of that. So this is shaping up to be an odd function. In the last example here, if I did the same thing, we'll start with 1 again. So I put in 1, I get 4, put in -1, I get 8. It's not really looking to be either case so far. Let's look at 2. 2 and 20, -2 is 16. So I'm not seeing either of those things happen. I'm not seeing the same y value come out. I'm not seeing the opposite y values. So this would just be a neither. Okay. So the table's a good way to get started. That is not the way we really want to do this in the long run. We're looking at proving things more so than you've probably ever done in math this year. We've got to get to a point where you can prove beyond a shadow of doubt you know something is true. And we usually do that by algebra. So let's take a look at another function and figure out whether it's even or odd. Okay? Might be a little bit too much information at one time. Let me pull the screen up. So here's the function. Let's figure out whether it's even or odd. And I'm going to ask you to do it in a couple of ways. First, by plugging in a couple of points. Okay? This is kind of in line with the table option. It's a good way to get started and see if you're on the right path. But this doesn't prove anything. This is kind of just getting started. But let's just see what happens. So I'm going to stop and magically come right back with what these values are. All right, so when I put these in, I'm getting 1, 3, and negative 1, negative 3. So 1, 3, negative 1, negative 3. That's kind of seems like it might be an odd function. So let me ask you, and if we were in a classroom, I would ask us as a discussion, we'd talk about it a little bit, but how many points do you think I need to graph this way to know for sure whether it's even or odd? Maybe pause there and just think about that for a second. All right, so the answer to that, you would need an infinite number of points, which will take the rest of your life and you'll still not be done, so a very inefficient way to go about it. So let's try proving this by algebra, okay? So we've got a definition, and both of those definitions, I'm going to flash back to those really quick here. Both of these definitions hinge on you putting in negative x. You plug in the opposite x value and see what comes out. Now, three things can happen. You get the exact same thing out, so it's even. You get the opposite of what you started with, which makes it odd, or neither of those happen. And if you're not sure what I mean by get the same thing out or opposite thing out, I'm going to point that out with the function here in just a second. All right, so remember, y is the same thing as f of x. So actually, I guess I should do an equal sign. So f of x equals this function. So if I put in negative x, let's run through and see what happens. So negative x gets cubed, and negative x gets squared, and I multiply negative x by 2, and then plus 6 at the end. All right, so let's think about what happens when we take negative x and we cube it. It's mostly all going to come down to the sign here, whether it's positive or negative. Well, negative cubed stays negative, so that's negative x cubed. All right. Remember your order of operations. Start with the parentheses, move on to the exponents. So negative x squared, well, that becomes positive x squared. So positive x squared times your negative 6 is negative x, 6x squared. All right. 2 times negative x is minus 2x, and then plus 6 will stay the same. So what we've got here now is f of negative x is this. So let's compare back to what it started out as. If it's the same thing as what we started with right here, it's an even function. If all the signs are exactly opposite, it's an odd function. If neither's happening, then it's neither. So let's kind of run through piece by piece. All right? It was x cubed, now it's negative x cubed. So it's kind of on the path to being an odd function. It's definitely not even right now. If it is odd, we're expecting to see the opposite of all of this. So negative x cubed plus 6x squared minus 2x minus 6. All the signs would change if it's an odd function. So let's kind of see if that's what's going on. So far, so good. Negative x squared, that's the opposite. Well, if it was going to be odd, I would expect this to be positive 6x squared. And that didn't happen. So we're done at that point. We know this is a neither. So if you look at a sine function, which even if you don't remember how to graph that, that's fine. Here's what it looks like. So pause for a second and think about what kind of symmetry you're seeing here. This one's going to be an odd function. Cosine, again, pause for a second, think about what kind of symmetry you've got going on here. So as you try different values for x, the y's are staying the same. That's an even function. Okay? You can probably sort of imagine if you're trying to do this stuff by hand, like find the sine of some decimal angle, which eventually you might end up doing. If you found one value and you can automatically know another one back here, that saves a lot of time. So, and if you hopefully remember a little bit about unit circle, that there's a lot of symmetry going on in the unit circle. So these are big time savers in calculus. And I'll scroll down to this last part, leave you with this. We're going to combine this idea of even and odd functions with series, and that's when you're going to get to some really interesting stuff in calculus.